It's about time to get started. Welcome to a new semester of VQMS. We're very excited for Fred Feinberg to tell us about his work on real-time 3D product design. As a reminder for the format, for those who haven't participated, the panelists should feel free to jump in at any time with any questions that they have. Everyone else, please use the Q&A feature to submit questions and we'll ask them on your behalf, and also feel free to stick around after the talk to ask any additional questions. So why don't you take it away, Fred?
Thank you, Dean. Before jumping into it, I think I should just say what this is about. What's the 30,000-foot elevator pitch, so to speak? And it's like conjoint is awesome. We all know how to do it, but it's not so awesome when we have to actually design how things look. And this is a way to kind of leverage machine learning, hierarchical Bayes, and all the stuff that's gone on in marketing and psychometrics for the last 30 years to try to accomplish that goal in something like real time without a huge respondent burden. And I'd like to just go through how we've been doing that. Just some preliminaries first. Thanks for having me and attending today. My co-authors presented here in something of a ziggurat fashion are Max Yiren, who's a mechanical engineer at ASU, Namwoo Kang at KAIST, and Panos Papalambros here at UMich. And you don't need a machine learning model. A simple logit is enough to see that these people are not from marketing. And that informs a lot of the way that this research went. We talk about product design, they talk about product design. We mean totally different things. And in a real sense, it's bringing these two perspectives together in one research project that we've been doing at this point for quite some time. It's resulted from a collaboration that's called Design Science. It's a PhD program and a master's program. Here at Michigan, Panos came up with this, I think it's a really snappy title. Traditional science studies the world as we find it, but design science studies the world as we make it. And as the panelists have mentioned, there will be pause slides for people to ask questions interspersed through. I just want to say that the first 22 slides, sounds like a lot, are just going to be a rapid fire review of things that almost all of us know about conjoint, but I just want to get us all on the same page. So this is an uncontroversial statement. I hope people can see my little mouse here. People care about how things look. Packages are always being redesigned. I find this one kind of funny, the word organic on Gatorade, but be that as it may. This is the same kettle graphically designed, but they found that changing the shadow on the second one caused people to think it looked much, much better. This is one of the highest rated kettles on Amazon, looks quite different, and probably the single biggest design fail in marketing history is the Edsel. People took one look at it and said, my God, it's hideous. This is what we want to avoid. We want to do pre-market forecasting that gets us away from the my God, it's hideous thing. So how can we do that? Well, we've been asking people for a very long time to tell us what they would like. All of you teach this in survey design. We might say, in choosing a restaurant, how important is decor, and location, and quality of food? People can answer these questions. They give us answers, but they don't really tell us anything. They don't tell us what to actually produce, like location. How close should it be? What price should we charge? What kind of food do we need? How do we trade these off? None of those gives us answers to the question we really want. So what do we do instead? I know what you're all thinking because we all teach it, and that is conjoint. This is like our greatest hit. I think it's in 4 of our MBA classes here at Michigan in marketing. It's used all over the world, at least 10,000 studies a year. And the key ideas, I think, are that we give people product profiles, not just little attributes at a time, and we ask them to do some type of trade-offs. Here's an example of one that I got from a website in India, and I picked it because I think they have much better snack names in India. Like this one is called Mad Angles. It's kind of like the chip for deranged geometers or something, and their masala madness flavor is only 7 rupees. You can't go wrong. I would pick that one. But the point is, I would give you 4 product profiles. You would pick the one that you want, and if we do enough of these, regardless of how we get the information, we're going to try to extract part worth values. And if price is one of those, we can convert it into willingness to pay. This is a mainstay of what we do in marketing, regardless of how we elicit the initial data. But there are a lot of elicitation methods. We started out years ago, the early work was on ranking, and we found out that that is slow. Giving people 20 profiles and asking them to put it in order really doesn't tell us what we want in a reasonable amount of respondent time. Maybe a little bit better is a metric task where we can say, here is a bundle, here's a particular product, and how much do you like it, or how likely are you to buy it? The problem is there's no trade-off here, and there's a lot of scale usage heterogeneity. A number of papers by Greg Allenby exploring problems with that. For instance, better. And the two that I'm going to try to leverage today are a binary trade-off strength. So I could say, here's one car and here's another car. Which one would you buy? And this is more granular information. People who are purists and like choice-based conjoint would say, no, you should force them into a binary choice. Well, this is a generalization of the binary choice. But the nice thing about something that's binary, or should I say multinomial if there's more than one, is it's scale-free. The scale is inferred using either classical or Bayesian methods from the choices, data augmentation is one way that we could impose a scale on top of this. I'm going to try to make use of both of these in the talk today and the task that we actually asked people to do. And I think these are two of the best modern methods for elicitation. Once we get these, we can say, okay, here are attributes, price, miles per gallon, acceleration. What are the part widths associated with each of the levels inside those? And with some assumptions about regularization, we can put curves through these. I wouldn't do it with 3 points. That's ridiculous. But assuming that we have a lot of levels and we have different people and maybe an adaptive design, we can decide to put curves through this that allow us to interpolate for internal values that were not in the original conjoint tasks. And if we do that, why do we do that? Then we can do design optimization. I could say, here's two products we're thinking of making. They have levels that were not part of the original set that we tested. But using interpolation, or I think a better way to think about it is some regularized heterogeneous hypersurface, which is already in the literature, we can say, well, here's the utility for product A, here's the utility for product B. There's some error model floating in the background, and I'm going to get to that later because it was a major criticism of what we did in the first round of this paper. But the point is, if we collect this right, we can then say, how do we optimize the product in terms of these specific attributes? And we can use splines or Gaussian processes and hierarchical Bayes and all that fun stuff that's been developed in the literature over the past couple of decades. So just a quick tour of some of the things we can account for, especially with an eye towards what we're going to use in the talk today. We can have multiple information sources. And I'm going to steal the next slide from Ellie Feit's dissertation paper. She came up with a very general method to fuse different sources of conjoint data. But the part that I specifically want to emphasize is this scaling parameter. This was first brought up by Louviere and Swade and Louviere quite a long time ago in 1993. They pointed out that different types of questions in different data sources have different error scales. Sometimes people give you a lot more information with one type of question than with another, and we have to leverage that. And I'm going to come back to that a bit later today. Another thing is we want to be able to develop orthogonal designs, preferably with utility balance. I'll get there a bit later, for both metric and scale-free designs. And scale-free turns out to be quite a bit more of a challenge. I think the most important one is that the design is adaptive. And the idea behind adaptation is I use answers that you've already given me and answers that other people have already given me to generate my next query for you. This cuts down dramatically on the amount of time it takes me to zero in on, if I can use this metaphor, where you get the big rises in your S-shaped curve. That indicates where trade-offs are very salient for you. Parametric versus machine learning approaches to query generation and training. To grossly simplify something that's much more complicated, parametric models are slow to estimate, especially with Bayesian methods. ML approaches can zoom right to a really high density part of the space and generate queries quite well. And we want to be able to leverage that technology. There's also different kinds of attributes. Some are interval scale, they're nice and smooth. Some are ordinal, like price. Most people like to pay a lower price than a higher price. And some are nominal, things like color, or do you want a sedan or an SUV? We need to be able to handle all of those. If we want to get fancy, we can also overlay Gaussian processes. There's a spectacular paper by Ryan Du and Asim Ansari that I recommend that everybody read on how to do this, just because it's natively supported in Stan. Anybody can do this fancy Bayesian non-parametrics today. Or if we want, we can fit splines of the type that I just showed you before. Incentive alignment, a paper by Ding and co-authors. Basically, people spend fake money too easily. We want them to have skin in the game, money on the table, all those nice metaphors. We couldn't do this because it's cars. It's hard to say, we're going to force you to buy one of these cars at the end, the one that you design. We'll build it for you and you're going to pay for it. So if someone could think of a good way to incentive align the car task, we would like to hear it. But probably most important is we've got to have individual level preference heterogeneity. People like different stuff. So any paper that doesn't incorporate this is just wrong. We're going to use hierarchical Bayes models. If you want to get even fancier, you can use Dirichlet processes within the hierarchical Bayes process. So just to make it clear, today I'm going to take the first 5 of these along with the preference heterogeneity. And all of these things are going to come up in how we do the model and how we estimate it, and then how we do the optimization. So there's several parts to it. So starting where I started before, people care how things look. How can we get at that? I'm not going to spend a lot of time on literature review. All the slides are online. I did that on purpose in case this goes by fast. There's an awesome review in the paper by Dotson, Beltramo, Feit, and Smith, which does a lot of what we do, but with static pictures. And there's some pluses and minuses to that I'll hope to touch on later. But the idea is that we've known for a long time, 30 years, that styling is really important in product design. We also know, there's some work by Wes Hutchinson that pioneered this. Why are some visual designs more appealing than others? And what are the psychological processes that underlie that processing? Well, a lot of this has been done in marketing. In engineering, they have something called form, which is a lot like what we call design. In fact, there's so many words for the same thing. There's shape, there's design, there's silhouette, there's profile, there's appearance, there's styling. But all of this is pretty much this holistic gestalt. I got those 2 words mixed up. Holistic gestalt thing about how things look in the real world in 3 dimensions. And the fact that humans can make snap judgments. I like this, I don't like that. And there's another way we can back around this that I'll get to in a moment, but we really just want people to look at things and say, I like this, I don't like that. And the model does everything else for us. And that's what we're working towards today. So this is what we do inside every conjoint model. We say that you have some preference, and it could be linear or linearized, and it means linear in parameters. There can be interaction effects. There can be arbitrary high orders in there, as long as we can write it as a matrix product. And here we're going to just put some functional attributes like price and miles per gallon. Of course, there can be more in determining what you like about a car. And here's the point. We know that this works really well for certain kinds of attributes. Anything that's tangible, you can feel it, like the weight or thickness of a phone that you're thinking of buying. Something that's numerical or fungible, like price. I can't feel it, but everybody knows what a price is. Everybody says, oh, 1-year warranty isn't great. Maybe a 3 or a 5-year one is better. Very easy to, in other words, conceptualize. All of these things we know work well in conjoint. If you want to learn more about this, 2 papers that I would recommend, one from marketing is by Kim, Park, Bradlow, and Ding on something called Pi. It's a really nice paper. And another one from engineering about crux and sentinel attributes cover this whole space really well. I think it's really fascinating. But what doesn't it work well for? Experiential, and I got this from UMTRI, the University of Michigan Transportation Research Institute. They really want to know, because they work with car companies, what is a quiet ride? Now you might think, well, we can just measure that in decibels. Try putting that on a conjoint. Do you prefer this car with 71 decibels or this car with 74 decibels? I mean, that's just not precise. It's psychoacoustically defined. I mean, decibels have to do with pressure on your eardrum. What could be closer to the ideal than that, except it means nothing to actual people. There's something that is more holistic about a quiet ride. Geometric layout things. This trunk has 23,000 cubic inches of space, which I've seen in brochures. People have no idea, is that big? What can I fit in there? Can I put my golf clubs? There's no way to tell that. But above all, it's styling. How do things look? And people have been trying to do this for a while. It's gotten really stepped up in the last few years, and I'd like to give you a sense of why that's difficult. So suppose a consumer wants a sleek car. This car is sleek. I think you'd all agree. Why don't we conduct separate studies? We can say sleekness. What is the essence of sleekness? Can we connect it to other attributes that we can manipulate? And then we can use traditional methods, like we can say sleek is a combination of low profile and it has some taper to it. That works. It's been done. There's been a bunch of papers that have attempted to do this, and it's just possible to get that. But I think there's a big problem with this. you've got to know these attributes in advance. People aren't looking for sleekness or sportiness. I mean, those adjectives, we can answer them. I like a sleek car, but that's not what we're really trying to do. You either like a particular design or they don't. Why use these fake made up synthetic adjectives instead of just showing people actual designs? So that's what we want to do. And we want to figure out the rest heterogeneously, everybody gets different stuff, and efficiently. Consumers don't hate us because we make them sit there for hours clicking and clicking. That's kind of key as well. We know that this is possible because almost everything is designed by CAD today. We already have high-level geometric models of almost any physical product, particularly durable, high-involvement ones. Why don't we leverage that knowledge and information inside of the preference elicitation technologies that we use inside marketing? So we did this. I think it's a nice intro to this. We did it for dial readout scales. And you might say, how many dial readout scales can there be? It sounds boring. That's what we thought. And then we went to Amazon, and this is about 5% of them. They all look different, but the key is they don't work different. And they all rely on the same internal geometry, as it turns out. So we took apart scales, where we is Jay Mahalik, actually, who is the lead author on this. He's a professor of mechanical engineering now at CMU. And he actually figured out how all internal mechanical scales work. It turns out that if you do this, you can write down 14 equations that govern how mechanical scales can fit together. And it should make sense. If you want really big numbers and a high weight capacity, you need a big dial. So you can't say, I want all of that inside a tiny little package, unless you use a digital scale, which is more costly. So if you do this, it means that we can ask consumers what they want, but we build things that are actually buildable. So telling people we can fit all of this stuff inside a small package, we would say we can't build that. And we used a traditional conjoint task to do this. This was a very boring task. I was younger and didn't know what I was doing. We asked people to fill in 50, not 15, 50 of these in a row. And you would literally start to lose your mind after a while. I just have to pause for this. You know, we have to ask people for feedback if they have complaints. I got the best snarky feedback ever on any study for this one. One person wrote to me and said, if I had only an hour to live, I'd want to do your study again, because it would feel like an entire lifetime. And I thought that was really creative feedback. Unfortunately, it wasn't very positive. We've learned our lesson. You don't ask people to do 50 choice tasks. And that's something that guided our work here as well. We estimated this model using multinomial logit. We got beautiful part works. We did it heterogeneously. Everything worked out well, and we were able to design an entire line of scales. So we knew that this worked. It's possible to do product topology models and to optimize conditional on them. What we didn't do is we didn't optimize the design using anything adaptive. We had to ask people 50 of these horrible things in a row, because we really didn't know how to do that back then. So that's a quick overview of the whole literature. I doubt there's too many questions right now, but I'll pause in case there are. Anything? I'm seeing, that's great. Okay, there'll be a lot more questions later, so I'm going to jump into it. So what did we do? We said, let's jump from a bathroom scale to a sedan, arguably the most complex product that people buy outside of a home. And we found that it's possible to do a pretty good job capturing the space of shapes of the sedan using 19 design variables. And again, when I say we, this was Max, who's an expert on car design. Why 19? Yeah, you can put in a few more if you want. You can put in a few less. This is a judgment call. But we found that you can capture the space of existing sedans quite well visually using these. There's no color, there's no internal design. It's just the external part. And you say, what are these points? Well, here you go. Here's a description of them. It's the forward and vertical displacement of the windshield. This is very boring, isn't it? So I decided when I was putting the talk together, it's about visuals. So why don't I try to be as visual as possible? So at several junctures, I'm going to have to beg the indulgence of our discussants here. I'm going to use them as kind of a Greek chorus type metaphor, even though they skew a little more Eastern Bloc than Hellenic. But they're going to come in and ask some rhetorical questions that I will then answer. So here they are. It's a nice looking group. Naming those 19 variables isn't doing it for us. What effects do they have visually? Wow, that's the same question reviewer number 2 had. What are the odds? Let me stop there. I've had good review teams before. This one is out of this world. Thank you, Sudhir, for picking them. Reviewer 2 in particular wrote 8 single space pages. He checked, or she checked, all our algorithms and found, like, why don't you do this? I've never seen anybody put in this kind of effort. So some of what you're seeing here was due to this person's insight, whoever you are. So let's have a quick look at the median car. That's in the middle. And what happens as we move these variables around 25% in each direction? So I think that's a lot easier to see. So here's the average car. Everything is at its median point. If I move the windshield hood midjoint point a bit forward, you can see the front of the car has gotten a bit shorter. And here it's got a bit longer. It's subtle, but it does change the look. And here is the median car again. I'm now moving that point up a little bit. Here, I'm moving it down a little bit. I picked these because these turn out to be very important in terms of people's aesthetics. I'll show you those weights later. Here's another one that was important, the displacement of the front hood midpoint. And here's another, we can rotate these cars very easily. I'll show you that. Here's that design. What happens if I move the hood a little bit forward or a little bit backwards? What happens if I do that vertically? And again, the point is you shouldn't have to figure out what the changes are. You just want to look at it and go, I don't like this, or I do like this. That's the whole idea. So this is a complex design space. It's not 2 to the 19th. We're moving all of these continuously. So it's a super high dimensional space of potential shapes. And I'd like to show you how that works. But before I do, we're also going to add traditional marketing things because that matters to people. If I had this to do over again, we would add more. This was more like a proof of concept and we didn't know how quickly we can optimize. So we just put in 2. We put in price and miles per gallon. How did we pick these points? We went to the 10th and 90th percentile of those that were available on the market. So at the time that we ran these studies, like 4.5 years ago, $23,000 was in the 10th percentile, 31,000 of the C car class, as it's called, of sedans. And we just picked those. Again, I would probably want to do more to make it more realistic today. How do we do all this together? So here's our new model. We still have utility, same as before. We still have all the functional attributes, same as before, but now we've added in 2 new things. How important is styling to you? Some people might not care about styling. And then there's a style model. Which styles do you like? You might say, for instance, I really like this style better than that, but I'm not willing to pay for it. You can have preferences, but not enough to actually cause you to give up money to get it. So we also need a weight on the style preference as well. At this point, I can't help but go into my favorite tweet probably ever. Arvind Narayanan is a computer science professor at Princeton, and this has gotten millions of upvotes. Tech buzzwords explain. AI is regression, and big data is data. Then there's a few more, and then the one I want to focus on, data science, statistics done by non-statisticians. Yes, it's a little bit snarky, and he's actually not a statistician. But the point is, we did all of this with ML stuff, and the review team came back and said, no, you need an actual error model. We need posteriors, like how accurate are your estimates? Just coming up with the highest point on a complex surface and saying we're done isn't really going to do it. So in the end, we want to use ML as much as possible because it's fast and it generates these queries and trains the model quickly, but circle back at the end with a full strength hierarchical Bayes treatment that's specifically tailored for these data. So I thought that was a nice way of introducing it. So why don't we just use a lot of the stuff that's already gone on in the literature. HB, it's been used for like 25 years. HB is great for weights. I'm going to use them to get weights. HB is not good for style. We have to train the style model. And why do we have to do that? Because style is holistic. You don't say, ooh, I really like the displacement of this hood. That's ridiculous. You just want to look at a picture and say, I like this, I don't like that, I can't explain why. It's high dimensional, it's super nonlinear. It could be that when I put 3 things together that you like, you suddenly don't like it anymore. And we need to generate the conjoint queries on the fly. That's the challenge. If I had a supercomputer, I can put in anything I want. But
Fred, can I ask a quick question? I think this is jumping ahead probably a little bit.
That was scary.
This is really cool, by the way. Really cool. So I was wondering if you're going to try to estimate the lambdas also as individual level parameters.
Yes. We're actually going to do something a little crazier at the end. We did that in the version of the paper that's online now, and they asked us to do something even more ambitious.
Also,
so yes.
as with HB, with some shrinkage to the mean.
It depends. Yes, there's a
or some.
It's not going to be a multivariate normal distribution that I'm going to use.
Some version of it.
Yeah, because that means everybody kind of converges on the same thing, which is exactly what we don't want. Yeah, but yes, that's exactly the intuition. Was there another question?
Very cool. Thank you.
Maybe I should jump on and we have question slides. So here they are again, our Greek chorus. There's a lot of stuff lying around. What are the substantive, pragmatic, and modeling problems exactly? Awesome questions. The first one, what is substantive? We want to pull out how things should look within conjoint. That's our high level goal. Pragmatic, we have to do it adaptively and quickly. We could do this amazingly well if people can wait a minute or two to get the next query. They can't. We set an absolute limit of 10 seconds from the time somebody clicked till the next query is generated, which places some limits on what we can do inside of a standard system. And the modeling problem is we want to leverage the best aspects of machine learning for active query generation and HB for a parametric or non-parametric account of what's going on. So hasn't quite a bit of this been accomplished already, like by some of us? Are you coming up with new algorithms for everything? So the first question, absolutely. And to the second question, no. We want to leverage vetted, scalable machine learning algorithms for query generation and model training, and then circle back with HB for the best design. So I want to do a quick tour of some of the algorithms we're going to use, but I just want to, if I can get up on a soapbox for a minute, it drives me a little nuts in marketing where they want you to develop everything anew. I don't trust new things. I trust things like LDA, which have been quoted in 25,000 papers and have 50 different R implementations. I know that if you use that, you might make a mistake, but at least you're using vetted code. So we're really trying to use algorithms that we know work, but we make some tweaks to get them to work fast for our particular problem. And that's where some of the black art, I think, comes into it. So a little bit about estimation query generation. This seems a bit like a fanzine to Olivier Tubia and Theos Evgeniou. They did a lot of the early work in this. Well, the really earliest work was in hierarchical Bayes. Peter Lenk and Wayne DeSarbo did hierarchical Bayes conjoint analysis in '96. And then there was the whole Allen B. Rossi and McCulloch juggernaut that came in the next 10 years where everybody did HB. But I love Bayesian stuff. Most of my work is Bayesian, but it is freaking slow. You're not going to use it in real time to actually generate queries. Olivier and his co-authors and then some other people came up with really excellent ways using the polyhedral methods first that were developed by Karmarkar in the 80s to do this a lot faster. There was no really great error theory for that, which is going to be a problem for us at the end, but it works very well. And the particular thing we're going to leverage a lot is the SVM mix that was in Evgeniou's 2005 paper and another one by Fan that I'll talk about later. So for us, the form preference model is going to be an SVM mix, but overall preference, when I come back at the end, we're going to use hierarchical Bayes. So it's a mixture of a lot of these different methods. Is it the absolute best methods? No, I'm sure it's not. The whole point is that this can be modular, and as better algorithms come along or faster computers, we can switch to something better. I don't think this is at its core an algorithmic problem specifically, just showing you can do it. Generation is trickier. We have to generate the next query. You give us an answer. We have to come up with something that explores the space for you. And then we also have to train the model for everybody else. So there's two phases in this. There's a lot of work on this, some of it done by Daria and John, which is why they're panelists. And we're going to use an adaptive metric paired comparison SVM mix and a bit more controversially, genetic algorithms, which many people think are very slow, but they're actually not if you use them correctly. And they can deal with non-convex problems particularly well. Again, I don't want to make this all about the algorithms. They have been in the literature. We try to adapt the best ones that would work for our problems so that we can get answers back to respondents as quickly as possible. So here's the idea. We want to figure out these individual weights. That's what HB is awesome at while training the styling model. and figuring out the next query for you and training the population model. So there's a lot of pieces there. So our approach is to break the problem up. We're going to do an adaptive query for the style estimation. How should the product look? And then a different adaptive query, and I'll do more on this in a moment, to relate style to the marketing attributes. There is a specific reason why we break it up, and I'll get there in a moment. We're going to alternate these, go back and forth. We just did that because we thought it would help with respondent boredom. After each round, you give me all your data, we update the population model. And when we collect all of the data, we use hierarchical Bayes for the design optimization. And I'll have more to say on each of those pieces in a minute, but that's the general approach. And naturally, you might ask, break up, how? Because I couldn't resist this cheesy 70s song. Breaking up is hard to do. We're going to use something called a bi-level adaptive query. And that sounds made up. What's a bi-level adaptive query and why is it useful? It indeed does originate here. One could say it's made up. Let's have a look, shall we, at what one of these things actually is. So the key idea is style is hard to measure. So we want a bit more information. So we decided to use a metric strength of preference scale. We were afraid that given the very high dimensional nature of the design space, just asking people for binary comparisons, 15 of them per person, we would not be able to explore that space well. Why did we go with 4 points? Just because we thought that more points would be complicated for respondents. There's nothing special about 4. The econometric model that I'll show you at the end can accommodate any number of scale points quite seamlessly. This is the key point. This allows style measurement even for people who care much more about other attributes. Let me just give you an example. You're really cheap. Every profile I show you, you always pick the low price one. I've just learned nothing about your style preferences. You ignore it. You have them, but you don't factor them in. And adapting, hoping that I could adapt in this super high dimensional space quickly enough to figure out your style preferences, that's a dicey proposition. So this was a research decision. We wanted to make sure we can measure the style pretty well for anybody, because I hope this makes sense. We want a heterogeneity model for this. And maybe having 20, 30, 40% of the people not giving us much information means that what we learn about them will all be taken from the heterogeneity distribution. That's a bad idea. We want everybody to tell us what their style preferences are, even if they don't care about styling, which I think is what Daria's question actually was trying to get at. The purchase questions, which are over here, are going to allow a non-metric, so binary choice trade-off between style and conventional conjoint attributes. So we show them pictures of cars, but we add the conjoint attributes in. So we think this is the best of both worlds. We get detailed information on the style, and then we have a non-metric choice that is typical of more conjoint applications. So we're going to put HB at the end to weave it all together. And you might say, oh, this sounds intriguing, but can you make it work in real time with manipulable 3D geometry? That would be really impressive. Gee, I'm not sure unless, oh, wait, there's the website address that was sent out. It works and you can try it out yourself. This is not some secret thing, but don't do it now because I have an animation for how it works on the next slide. And I hope this works over Zoom. So I'm going to click it and I'm going to extemporize what the person who's doing it might be thinking. And here's the cool part, ready? They can move it. They can explore the design in real time. It's being generated in Java. So it allows people to see it from every angle, because otherwise they would just focus on the things they can see. We wanted them to get a sense of the holistic 3D geometry, which is what I think is actually fairly new in this approach. They have a metric choice. They like the one on the right better. And we're like, you like the one on the right better? Are you willing to pay for it? Because we just stuck a higher price on it and worse miles per gallon. That's utility balance. So we know from the population model that people don't like higher price or MPGs. So, and now it went back to the server and it generated 2 new designs. And again, you can make a metric choice. Which one do you like better and how much more do you like it? Make sure to swing both cars in every direction before you make your decision. Which one will they pick? Can you guess? Correct, the one on the left. And then they confirm it. And again, we ask them, are you willing to pay for that? And the idea always is we use population information, U information, and searching using a method that I'll get to in a bit later to try to come up with the optimal query for you next. Not just for you, but to actually train the entire model. So there's a lot going on here. And the key is we don't want to ask people to sit for this forever. We give them 15 pairs of questions, so 30 total, which is already getting fairly high. But amazingly, this works pretty well with that amount of information. So just to review it slightly more rigorously. So, oops, I was quick on the trigger there. So we ask them a styling question that is a metric choice. We train the styling model using a rank SVM, and then we generate a sample pair that should go along with it. And we generate a non-metric choice, which has the same ones in it. It's paired typically with, this is the one they like better. Notice that it gets worse stuff paired with it because of utility balance. We use that to train the full model. This gives us a sense of how important the attributes are to them and styling is to them. And they do this 15 times. And in fact, we keep going back and forth. To be a little more accurate, we go back and forth between the two types. Sometimes they get the metric trade-off first and then the non-metric. Sometimes they get the non-metric and then the metric. And this is just to keep respondents interested. Also, we were a little concerned about locking them in. If they always answer the style question first, they might try to justify that. Well, I just told you I like this better and I don't want to seem cheap, so I'm going to pick that for the next one as well. These were all design decisions, and we did a bunch of post hoc tests to see whether those were reasonable or not. I'm not going to take you through this whole thing, but it's the exact design idea. All this says is you start, you do a bunch of these queries. When you're done, we train the whole model, and then somebody else comes along. And when everybody's done, we take all of their data and we throw it into a hierarchical Bayes model. So there's two phases. You are adaptive, train the population level model, then the next person is adaptive. And when we're completely done, we're like, thank you. We have data on hundreds of people. Now let's throw it into HB, a model that we built specifically for that. So that was a lot of stuff that I threw at people, and I'm doing not horribly on time. This is our second pause for questions. Are there any?
Yeah.
Yeah.
There are quite a few. So first, Kanishka has a question. Could the dimensions for the style variables be learned as opposed to defined by the researcher?
Well, anything's possible. I think if you use a GAN or something that's a bit newer, yes, that would be not just a high dimensional problem, it would be definitionally non-parametric, which would mean you'd need to have some way of jumping across the dimensionalities of those spaces. I don't know enough about what people are doing with visual learning to say whether that's feasible in the 3 to 5 second window we have for generating. I think though that Alex and Artyom will have some insights on that because they've done that kind of thing, and John. So I think it can be done. We just didn't even think of doing that because we already had expertise in building a fully geometrized parametric model of sedans. For a new product, we'd have to start over completely. And that may be one of the advantages of what you're asking. Next.
Justin Huang has a question. Would there be any challenges to introducing a midpoint in your preference scale that says the same or no preference?
No, the model that I'm going to show you is fully general and can accommodate, in fact, both parts of the model can accommodate any scales. It's all Stan. So anyone who wants to use it can download it and do it.
Oded Netzer has a question. Does the double evaluation on style artificially increase the importance of style?
No one's ever asked me that before. So I'll say, no, of course not. What a crazy question. No, I have no idea.
Like that was what you were getting at and saying that you were worried about asking it beforehand. It'd be a similar sort of effect. Do you see any of that order effect? Maybe that would be a way of
No, we tested for that. But I think what Oded is saying is, maybe I'm putting words in his mouth, which is a bit unsanitary, but if we ask 30 questions that have style and 15 that have the attributes, people might get the idea that style is more important and we might get a demand artifact. And I don't know about that. However, we did actually, I'm going to show you, we did have a condition where everybody only got they got 30 questions with all the attributes in it. And that does not work as well, actually, surprisingly. But I didn't check for a bias, and I should do that. So that's a really good question.
I just have a follow-up question on that, actually, since we're talking about it. Over the course of this task, are people implicitly thinking that you want them to care about style, and as a result, they're is there some evolution in preferences from the beginning to the end of your survey? I guess maybe
that's the question Daria should have asked, since she's the evolution of preferences matriarch. We did check for that, but with 30, it was very difficult to find a trend. So the fact that we could not reject no trend doesn't mean it's actually not there. I think if we had gone on longer, by the way, people were able to do a trial round just to get used to the technology. I learned a long time ago that if you throw somebody into a complex task, the first few things they do are purely exploratory, and you can't use that data. But I think your question is deeper than that. It's whether or not people start learning things about what they like. And we could not reject that when we looked for a trend. But I would guess that if we had longer sequences, we would find it. Other questions?
Okay. There's a question about the interaction of how much you care about style with how much you care about price. So have you thought about that?
Yeah, there's a multivariate distribution across those individual weights, so we can capture that.
Okay,
yeah.
Got it.
Yeah.
There's a question about whether you did any pretest to ensure that the auto-generated styles differ enough to be visually discernible.
Oh,
is that a
we
part
do
of your
pretests? To put it mildly, yeah, the problem is we're going to use a hard margin SVM, which, without getting too technical, doesn't always give an answer. So we had to pretest the heck out of this to make sure that the generation always worked, the training always worked, but also people didn't start getting styles that, because of utility balance, were so close that they couldn't discern them. And that's a judgment call. But because the algorithms had an exploration component to explore the space, we weren't that worried that they would start generating things that were arbitrarily close. So there was an enormous amount of pretesting. Does that mean that no respondent started saying, whoa, these things look alike? No, I can't guard against that. There was no minimum distance norm put in to ensure that nothing like that happened.
There's a question from Glenn Urban about the role of art in styling.
Art?
Yes, and I don't know what that really means.
Oh, Glenn, the famous sculptor with the nicest office ever at MIT. There is a big literature on that, but I found that, I'm going to be an awful person, I find it a little bit factitious and was not terribly enlightening. The idea that you can like throw a Picasso painting into a machine learning model and it says, wow, that's really awesome, and an imitator into it, and it says, no, this is a garbage fake. I don't see that happening. And I don't mean to say the question is easy to answer. I don't think that the really aesthetic elements, we haven't captured those. Like, these are really stripped down cars. There's no color in there, for instance, which is very important. And, you know, a lot of the other elements would need to be layered on, which is, I think, actually where the stuff that Alex and Artyom has done has taken that one level beyond. But if it's systematizing aesthetics, I don't personally think we're anywhere close to that. I don't know if that exactly answers the question, but it's the best I can do based on my nerd's reading of the literature. Other questions? Should I go on? Because we're, okay.
Dean, you said you were gonna, oh yeah.
Yeah, maybe I should jump on, and if there's other questions, we can get back to them a bit later.
we can come back to these. Yeah.
Okay. I didn't tell you what the style model is, right? Like, what the heck is that? How does it depend on the 19 variables? How are the designs generated? Whoa, there's a tough crowd. I can't get anything past you. So there are two answers. It's modular. Other style models can swap in. This is not unique, obviously. There's a lot of choices that are being made. It's really, really nonlinear. And there's a whole paper that we relied on to do this. But the idea is the 19 variables that we can move around, they actually translate into 26 control points that are manipulable. And then there are fixed control points, like the car has to fit together. If we pull the front out, the other parts have to move a little bit to conform to that. So there are certain points that are fixed. And what happens inside the program is all of this together generates 30 B-spline surfaces that are auto-generated, and each one is controlled by 9 control points. Why 9? Just because. This is an art, not a science. We're trying to get all of this to happen in real time and generate something that is always a symmetric, closed, and smooth design, one that joins up. These define half of the car geometry, which is then mirrored for the other half. And the wheels and tires are created independently. We don't put mirrors on. There's no pinstriping. Like a lot of the things that people actually like, to get to Glenn's question, are really not covered here. Could we do this today with a faster computer? Yes, I think the answer to that is yes. But we wanted this to work within 3 to 5 seconds. I keep emphasizing that. Anything that might slow it down would cause respondents to go, I'm out of here. This is a really boring, slow task. So a lot of what you're seeing is really a concession to that. If you're interested in this, and all of this is in the slides that you can download, Max, the lead author on this paper, and Panos, the other co-author, wrote a whole paper on how you can do this in general for different designs, and it's complicated. We leverage that. There's an art to it, and unfortunately, it has to be done separately for each complex durable, which is the first question that I was asked. Is there a way to learn these preferences just starting from primitives? And I think, again, the answer is yes, but you would need a much longer sequence of choices to be able to auto-learn what these things are supposed to be. What about the algorithms?
So could you tell, so how many
wow,
parameters?
It's like so loud. Sorry, what's that? Sorry?
So I was wondering, so how many parameters are there? So there's 26 points and there's 30 splines, but overall, how many parameters per individual does the model have to estimate?
It depends what you call a parameter, because to a Bayesian, a parameter is a different thing from you mean like things you can control? There's 19 points that can move in one of 2 directions. So there you can say that there's 19 sliders that completely define the car. But those points don't include the fixed control points that makes the car actually come together. So that's part of the trick of it. So there's a whole nonlinear transformation that actually gives rise to the car. But if you want to think of it in a doctrinaire way, there's 19 things that can go from 0 to 100, so to speak, that allow you to get the full shape of cars. And the question is,
on the preference side, I think, which is maybe part of the question, the individual level preferences, because they're parameterized by a spline, and they're shrunken, so obviously they're not just totally free.
I didn't parameterize them by a spline. They're actually going to be separately, individually estimated points. You can put a spline through them for optimization post hoc.
I see.
Yeah. I didn't do that as part of this because they were fixed control points. We could adapt those as well. We just thought that might be confusing to respondents to be told this car is $27.63 thousand. So we kept it to the kinds of prices that people are used to seeing. And again, that was a judgment call. I have a bunch of slides on the actual algorithms, but a lot of people tend to get bored or violent when I show those. So I've taken them out. I can get back to them a bit later, but it's really a series of non-convex optimization problems. We use a mixture of genetic algorithms and hard margin SVMs. One of the reviewers reasonably asked, why didn't you use a soft margin SVM that has much better properties? Because there was no general purpose commercial algorithm, not commercial, published algorithm that was guaranteed to work quickly then. But 2 years later, somebody came up with one. So I don't say that the way we did things in the paper is the best way. It was the way that was vetted and we knew it'd work, and we knew the theoretical properties, which I consider very important. We could have just made new things up, but then we really wouldn't know exactly how it worked. So this is just an idea of it, and how it all fits together is SVMs, rank SVMs for training, genetic algorithms for the query generation based on the utility balance that I showed you. So we want things that you like about the same, but we also have to search the space. So we did a bunch of cross-validation studies that figured out how that can happen, and we set the internal parameters based on a balance, so to speak, between being able to explore and being able to measure. And that's all in the paper, and it's pretty technical. And we did HB plus a whole lot of little tricks to speed things up that I won't delve into. Then we asked 100 people to do this, and we had 3 conditions. And each person answered 30 questions in total. And the three conditions were in one model, which didn't work so well. Everybody got both the style and the attributes. And you might say, shouldn't that work better? That should work better because they get more information, yet it didn't. We got a lot less style information, which I think was Oded Netzer's question. His was a little bit more subtle, saying maybe we're biasing people because we ask them more about the style, twice as much as about the attributes. But when we ask them about both, using standard DOE, this is a Latin hypercube design that's used all the time in conjoint studies, we got an okay hit rate, not great, not awful. When we split it up into the bi-level question, we did a lot better, actually, certainly in predicting the form preference. And this is a little odd because here we're still asking about the form preference in all 30 questions. Here we ask about the form preference in 30 questions, but in half of them, we don't put the attributes in. And suddenly, this is in a holdout sample. We can predict in a holdout sample much, much better. We didn't know how this would go. It was just on a hunch that if in half the questions we focus them just on the style, we would do a lot better. But we also do better in predicting overall preference. We tested this and we also said, well, instead of DOE, why don't we make it adaptive? Does the adaptivity itself, using these adaptive algorithms that zero in exactly for you, that makes things better, but not radically better. We found, ironically, that going from the single level question where everyone gets all the attributes all the time to the bi-level question provided a pretty big jump. And this was just a proof of concept. I don't think the bi-level question is some radical advance in our knowledge. It's not. It was just a way to focus people, maybe with some biases, as Oded pointed out, on the style itself, and it seemed to work. But I'd like to show you what we got out of it, not so much proving that it did a good job. So, John Hauser, yes, jump in.
The bi-level questions are actually very similar to dual response and conjoint.
Yes, it is.
Which we know really increases accuracy, in part because people are just more comfortable with them.
Oh, is that the reason? I didn't know that.
Well, there's two reasons. One is they're more comfortable with them. One is you actually literally do get more data. But Felix Eggers does a lot of work on this.
I'd like to follow up with you on that.
Germans love to study it.
There's all kinds of inappropriate jokes I can make based on that. So I'll
no.
I forget I said that, but it's recorded, so the internet never forgets. Anyway, let me jump on. What we really want to do is, what designs jump out of this? How can we extract them? And how can we get willingness to pay for design elements? And hopefully, we can link up marketing with engineering, which is what the whole point is. We have a bunch of engineers, they're awesome at these topological models, these geometric models. Can we throw all the stuff we know in about conjoint together to make them speak to each other so they can build stuff that people actually want? And the answer is yes. Can we put all of this into one big model, and do we see interesting groups emerge? And how do we do that? How do we formally use all the data? How do we come up with forms for a heterogeneous market? We need a new HB model to do this, unfortunately, one that combines a lot of crazy stuff. We need the metric answer for the form questions. We need the binary answer for the purchase questions. We need ordered part worths for the valenced attributes, like people like to pay lower prices more than higher prices. We need preference heterogeneity across respondents. That's important. We also want the forms to be handled and bundled non-parametrically. This is something that I go on about till people find an excuse to walk away from me. But the standard hierarchical Bayes model that regularizes everything to a multivariate normal distribution, that's pushing everybody towards the same thing. Yeah, there's variation, but it's unimodal, there's one hump. We didn't think that was appropriate for design. Why should you be regularizing everybody towards one design? So we used discrete heterogeneity instead, which turns out to be a bigger pain in the butt than the continuous heterogeneity, which I'll talk about in a moment. We also want to incorporate the design elements parsimoniously, and that's the next slide. And the Swait-Louvier scaling across question types. This sounds like a real pain. but it's not really with Stan. You can build some pretty good models with Stan, and all of this code is available, but we had to use radial basis function elements. And one of the reviewers told us how to do this. You might say, how? How did you do that? Not in this talk. Here it is. It's all on the slide. I don't want to run through this, but this took months of effort to figure out how many radial basis function elements need to be extracted to replicate the design in terms of what people picked. It's all explained here. It will all be explained in the paper, but your response to this should be, please don't do this to us again. Please just say we use 10 RBF functions and we'll believe you. So let's move forward with the fact that I can replicate this design model for the purposes of a choice model very well with 10 radial basis function elements. And if I do that, I can put together a hierarchical base model. And I hate when people put models up and don't explain them. So let me be graphical about this. Here's my styling question. Here's my purchase question. So we have our utility model for styling. It has only the radial basis function variables. Here's my utility model for purchase. It also has my price and MPG variables, my marketing attributes. Here's a ordinal logit model that's symmetric for the scale. I can have any number of points, which was Justin Huang's question. And I have a binary logit for purchase. I can make that ordinal too. The code will handle any type of responses for these. It's just fully general. And here are my coefficients. I'm going to come up with coefficients for my radial basis functions. I'm going to come up with coefficients for my price and my MPG. Those are my estimated quantities, along with Swait-Louvier scaling constants and a cutoff for the strength of preference on the ordinal symmetric scale. These are all of the attributes. I also have to specify priors. We use very diffuse priors because we're progressives. We don't like to put our preconceptions on other people. You can put whatever priors you want. The genius of Stan is priors don't need to be conjugate. So you can pick whatever you want. Put Cauchy priors on everything. You can be as nonchalant as you want with the priors. This worked like a charm if charms required several days of runtime. And I ran this model 100 times from 100 different starting points, 100 chains that were thousands and thousands long. Here are all the attributes. And you might say, what the heck is that? Here are my RBF coefficients. Here are my price coefficients, which are decreasing. Here are my MPG coefficients, which are increasing. Here's my class sizes. Class 1 is really big. And then there's some scaling constants and cutoffs. I don't expect anyone to get anything out of this. What does it look like? So here are the basic information, and here are the pictures. We can then, now this is a full model, it has errors, it has everything, and everything has a posterior. But if we go to the mode, the posterior mode, we can then figure out what each of the cars looks like for each group. And we can also talk about what's important in terms of the marketing attributes for each group. And this first group, which is very big, they seem to find style relatively important. The second group, which I call middle of the road, no pun intended, their style's important, everything's blah, they're right in the middle. Class 3 seems more price sensitive. Class 4 seems more MPG sensitive. These two classes, they don't really find styling very important. They're not huge. They're about 15% of the people, which might mean that Oded, I think, asked this is right. Maybe we are focusing people a little bit too much on the style. I still have to follow up on that. And I'm almost out of time, so I'm not going to take you through this willingness to pay exercise, and I'm going to circle back to questions at the end. Let me just say, there are many types of attributes that can drive choice. Some cannot be easily conveyed through design experiments. 3D rendering of design concepts is possible using an underlying geometry. We can use adaptive methods for real-time optimization, and we can quantify and trade off and segment them. But before leaving and opening up for questions, there's all of these post-hoc things that I knew I wouldn't have time for. People might think, what's next? And I already know what's next. Bernab, Hauser, and Timoshenko used GANS. And I'd love to be able to do this. I don't know if we can do it in real time, and I hope they will enlighten us about that. They input pictures of cars, and they generated images for which people would have high appeal and low appeal. That's kind of what we want to do. We just did it with a geometric model, and they did it with pictures. I know you can't rotate the pictures, but I like these better. They look real. The question is whether or not we can do all of this and generate everything and explore that design space in real time with these actual photos. And I'll skip over all the stuff about Detroit because we're near it. I will just say thanks. I'm exactly on time, and they said if I can stay around for questions after, if there are any that people want to ask, I'm happy to do that. So end of official presentation, and if you can stay for questions, awesome. Thank you.
All right, thanks. So for all the attendees, if you'd like to join the discussion, please raise your hand and we'll promote you to panelist. But otherwise, the panelists should feel free to ask questions. Thanks.
Can I ask a question, Fred?
Yeah,
If
sure.
you can, if you can, just to circle back to one of the questions that have been asked previously, I think Tesseri asked this question about like, maybe there's some interaction. I know you incorporated other attributes like pricing in the utility function, but if I'm reading correctly, I don't see like any interaction, which is probably what Tesseri is asking. Like, if I'm seeing this, the same person is seeing the same product with a higher price, would I have the feeling
better.
that, yeah, I now care about the design better or more?
We did test that. We put interaction effects in specifically in the hierarchical Bayes model, and we found strangely they were not significant. And that could be because there was only 30 pieces of data per respondent. So it could be an identification issue. So I wouldn't say there's never interactions, but we did not see evidence of those, even at the level of the hyperparameters. So we did explicitly test that, and you could thank reviewer number 1 for making us do that. Everything we did, all these questions are because the reviewers are doing their job. So yes, I think they're probably there, but we didn't find evidence for them. Does that make sense? Good, sure, thank you.